Hello and welcome. And we are covering the Carnegie Mellon University's Open Learning Initiative, OLI, uh, free and open logic and proofs course. And today we are going to be covering chapter 3. So this walkthrough is not so much on the content of the chapter, it's primarily actually focused on the way to properly solve the problems that are there. And that's because a lot of this involves, let's say, screen manipulation that people are not generally used to. So here you'll see how a lot of that works and why things are what they are. And that should hopefully help you out with your work. All right, so here we go. We have this question 1 here on the practice quiz problems in semantics. And so we see a question. So the job here is to symbolize the following argument using translation key provided, and then determine via truth tree whether or not the argument is valid. All right, so let's work out part 1. We have this paragraph here, and it says, lobbyists fight for a cause only if they are paid to do so. If a lobbyist is paid to fight for a cause, that lobbyist will not balk at using unethical means to advance that cause. Thus, if a lobbyist would balk at using unethical means to advance the cause, he or she won't fight for it. All right. And then we have a key down here. F is fighting for a cause. P is paid to fight for the cause. And B is balking at using unethical means. So let's work out this setup here. It says a lobbyist fights for a cause only if they're paid to do so. All right, now normally, when we have the word if in an argument, the way that it works is, let's say that the sentence said, lobbyists fight for a cause if they are paid to do so. What we would normally do is we would take the part that comes after the word if, and we would put that in front. And then we would take the first part of that sentence, we would put it in the back, and those two would be connected by a conditional statement, right? So if a lobbyist is paid to do so, then a lobbyist will fight for the cause, right? But this word only that's in front of the word if actually tells us that the sentence structure is going to stay exactly the same, right? So if means that you take the two parts of the sentence and you're going to reverse them. The phrase only if means that you're going to keep the parts of the sentences exactly as they are. Okay, so it's explained earlier in the chapter why that is. You can go back and look that up, but it's an important thing for this thing. So lobbyists fighting for the cause. Okay, so it's F. So if F, then P. So F, then P. There we go. If a lobbyist is paid to fight for a cause, then that lobbyist will not balk at using unethical means. So if P, then, and here's a kicker, the lobbyist will not balk. The key provided tells us that a lobbyist will balk. So that's if P, then not B. Okay. P, then not B. That should be it, if I get my letters right. Thus, if a lobbyist would balk at using unethical means, so there we have the word if again. This time it's just an if, not only if. So if B, then not F. B, then not F. All right. All right, so let's see if I can annotate this appropriately here. I'm going to use this, and we're going to use this red lining. Okay, this entire thing. All right, so one of the basic things that you can do is, if you look at these things, you can notice that we have the letter P appears twice in in the premises. So if F, then P, if P, then not B, right? So just like in math, or if you take in chemistry, right? Like when you have the same term repeated as a numerator and a denominator, and you're multiplying out the function, you can just cross both of them out. And so this gives us something like, if F, then not B. Okay, our conclusion though says if B, then not F. Now that is because, let me draw a line instead of this. Our standard goes something like this for conditionals, right? A conditional, let's say F, and in fact, you know what, let's make it A and B just because it's a little bit easier to deal with. So A and B. A conditional is true under all conditions, except there's only one time that a conditional isn't true. That's if the antecedent over here is true, but the consequent, the B part of this, is false, right? That's the only time that a conditional is not true. So we need to avoid this, right? If we end up in this situation, then we're going to have a problem. So now we're concluding the way that our paragraph is phrased. It tells us that B is true. Okay, so if B is true, then A over here can't be false. That's the only important thing. So, ta-da, that's why we have this. So that actually tells us that this outcome down here is the same as this outcome over here. So the if B, then not F is the same as saying if F, then not B. So that means that we arrived correctly down here. We can check our answers, wait for it all to load. Ta-da, there we go. We got the first part correct, and we got the second part correct. And now we can erase all the stuff that's on the screen right quick. All righty. All right, so that's how you solve those. Now remember that the idea of validity is an argument is valid if you get to the conclusion directly from the premises. So I give you the premises, if they lead you to a conclusion, and that conclusion doesn't have any crazy new stuff that's not justified, then it's a fine conclusion to have. So that's how we knew that it was valid, because this outcome down here is the same as the other one that we've get. All right, so now let's take a look at some lab problems here. I believe I pulled some up here for us. All right, so in the first one, we have to construct a truth table or a formula in order to determine whether it is a tautology, whether it is contingent, or whether it is contradictory. So these three terms are described in our chapter, but I'll just recapitulate them here really quick. A tautology is a formula where no matter what values you put in, the formula is still true, right? So it's a setup where you can't possibly be wrong. It's a great argument to have, right? No matter what happens, you're right. A contradictory statement is the opposite of that. No matter what you do, the outcome can't be true. It's always, always false. There's no way of making it true. And a contingent formula is one that's sometimes true, sometimes false. All right. So always check these things, by the way, before you start doing the problem, these terms, because you know you're going to need them. So go back, check, make sure you know what they mean, and then come back and do the problem. So let's go ahead and launch this one. All right, so we're going to build a truth table, then we're going to fill the truth table, and then we're going to run an analysis. That's actually pretty straightforward. All right, so the first thing we need is to enter an ordering on the atomic subformula of the following formula. So the atomic subformulas are the individual letters, and they're asking us to put in the letters that we're going to check whether they are true or false. Now, when you do this, you do not put in a negated version of a subatomic formula. So here, for example, we have P, you say if P, then not Q, not P and Q. So like you wouldn't put down, even if you had a not P, you wouldn't put down not P as a subatomic thing. You would just put down P as the actual atomic formula that we care about. So you put in all the letters. I just like to do them in whatever order they appear. It doesn't really matter. We have P and we have Q. Those are the two atomic elements that we have. We hit enter, so we get a table. All right, so the number of lines that you have in a table depends on how many atomic elements you have in a formula. And the way this works is the number of rows you need is 2 to the power of n, right? And n is how many different letters you have in the formula, right? So if n is 1, then it's 2 to the first power is just 2. If n is 2, so if we have 2 atomic statements like we have here, then it's 2 to the second power, that's 4. There's that. If you have 3, then you have 8 rows, and then if you have 4, you have 16 rows, and if you have 5 atomic elements, then you need 32 rows. You can see how this gets out of hand really, really quick. So yeah, this is where the digital version of this comes in really, really handy. Right, so now we know that on this, as we click on each of these rows, we know what the value of P is, and we know what the value of Q is. And now we have to figure out how that plays out in our formula. So when we click on that, what they do is they give us this tree that's been broken down. Now you should remember this parse tree from the previous chapter, right? This is all we were doing, constructing these things. And what you want to do is you want to start all the way at the bottom of the parse tree, and then look at the phrasing here, chase the truth up the parse tree. So you start off down here, and then you work your way all the way up until you have that one function left, then you plug that in. Right, so if P is true and Q is true, then P and Q, so if I put those two together, that would be true, right? Because a conjunction is true only if both of its conjuncts are both true. So that's great. So now I have the value for that. Now, if P and Q together is true, and then I stick a negation in front of it, well, not true gives us false. All right. And now we have a conditional up here. If P, that's true, then false. So if true, then false. Now you kind of have to stop there and think about how the conditional truth table works, which the chapter had discussed. In fact, this is the only time that a conditional can be true. That if the antecedent, the first part of it is true, but the consequent, the second half of it is false. So this kind of setup, if true, then false, means that the entire formula is false. Ta-da, here you go. So then we do that again. We have a conjunction, P and Q. P is true, Q is false. Well, in a conjunction, since both conjuncts have to be true in order for the conjunction to be true, and here we have one part that's false, this conjunction is false. All right. But now we take a negation of that conjunction, right? So now we say not false. That makes it true. And that leaves us with a true, so if true, then true. And that is a true conditional kind of statement. Now we can already see that this is not going to be a tautology because there's at least one field that's false. And we see that it can't be a contradictory thing because there's at least one field that's true. So this is going to be a contingent statement, and we already know that. Let me show you what happens if you make a mistake, because if you misclick like I do occasionally, you are going to end up in the following problem. So here we have false and true as a conjunction. That should give us false. Well, let's say you misclick on true. And so it tells us a conjunction is false if either one of its conjuncts is false. Great. Can I now just note that it's false? Nope. It's asking me to explain to it why this is false. Now, the way you do that especially if you can't really see that some of these things are buttons, like on my screen here, is each one of these values is something you can click on, right? So I click on true, and I click on false, and then I click on what the value should have been, right? If I had misclicked. And then that will actually let me enter it in, because otherwise it's just going to leave you stuck in that explain to me why this is what it is mode. All right, so now we have this conjunction is false, but now we're going to negate it. So if I'm saying not false, that's the same as saying true. All right, now, honestly, didn't really need to do all that work, because our top level function is a conditional. And we know that the antecedent, the P in this case, is false. Any conditional statement where the antecedent is false, the entire statement then has to be true. So we could have just clicked on that to begin with. Of course, it won't let us until we work all the way up. So here we have a conjunction with two false statements. That's a false conjunction. And then we negate the falsity, so to give us the truth. But it doesn't matter because it's false. If false, then true. That's a true statement as a conditional statement. And ta-da, there we go. Okay, so we have one value that's false, three values that are true. It's not all true, that would be a tautology. And it's not all false, that would be a contradiction. So it has to be the third option, which is contingent. In other words, it depends on what your values of the atomic statements are for what the value of the whole formula is going to be. And there we go. See if we'll get a couple more here really quick. All right, so we're going to need some truth tables and whatnot. The good news is, as we do this, it's going to actually get a little easier. So again, we're just gonna, I just type these out in order. So the first letter I see is the letter E, and I see C, and I see E, C, D, E, C, E, E, D. Okay, so there's only three elements there. So if we have 2 to the third power, that should give us 8 rows, and that's exactly what we have. Now, the first two lines here, this one here, the if D, then C and not E, and then the C or not E, those are both premises. And then the last column on the right is a conclusion. Now, we are wondering about the about validity and counterexamples, and we'll talk about that in a minute. So let's first work out all the premises and conclusion values. Right, so again, we're just chasing truth up the tree. So if E is true, and then we have not E, that would have to make it false. Here we have a conjunction of true and false, so that has to give us a false. And then our top level function here is a conditional. If true, then false. That's the only way that a conditional is false. So now we know what's that. So false, negation of a false gives us a true. Conjunction of two truths is true. A conditional statement with two truths is true. Good. Negation of truth gives us falsity. Conjunction of false statements is false. True and false gives us false. Negation of falsity gives us truth. Conjunction with one element of it false makes the entire thing false. And then again, we have if true, then false. That is going to be false. Negation of truth gives us falsity. Conjunction with at least one false element is false. If false, then false is true. Negation here gives us truth. That means that the conjunction is true. False and true is true. Negation of truth gives us falsity. That means that the conjunction is false, but false. If false, then false gives us a true conditional. True, but it doesn't matter because C is false, so the whole thing is false. False and false is a true conditional. All right, that's interesting. Let's take a look at the second premise, C or not E. All right, if E is true, then not E is false. This is a disjunction. Now remember, in a disjunction, you need at least one of the disjuncts to be true. They could both be true, but at least one of them has to be. Here, at least one of them is true. So there we go, that's true. It's nice anytime that the same truth conditions repeat, the table will fill in both the spots for you. True or true, it's true. If true, then the negation of it gives us false. False and false makes a disjunction false. And then false or true makes whole disjunction true. So here we go. Let's work out the last part here. It is, notice the top level function is a conjunction, so we need both sides to be true for this to be true. So that's going to happen kind of rarely. False and true is false. True and true, that's true. False and false is false. And true and false is false. Okay, so an argument is valid only if when you have true premises, you end up with true conclusions. So you want to look at these two rows up here. The I don't know how well you can tell, so let me just have one of these. Okay, you want to look at these two rows. And anytime that both of the premises are true, you need a conclusion to also be true. So let's take a look at where that is. Oh, whoops, circle. So they're both true here, and they're both true here, and they're both true here, and they're both true down here. Okay, so now you need the conclusion to also be true whenever both the premises are true. So this one checks out, but then none of these three do. So this is an invalid argument, meaning that your premises could be true, but your conclusion doesn't follow from them. So this is, we'll tell you this is invalid. Now it wants us to tell it at least one place where we found this sort of a problem, where the premises are true and the conclusion is false. You select any one of the rows where we have this problem. So we could select this one. You just have to select one, and then you're done with the whole problem. All right. I'm hoping that's easy enough to follow. Let's take a look at the last setup here. Okay, let's just do the first one. All right, so we want to figure out the truth tree and then determine whether or not it gives us a counterexample. Oh, this one's actually kind of important. Let me actually back up for a second. I'll go back. No. This is exercise 5.1. Let me just find that. It's really actually important to notice this little difference. All right, so here we are on exercise 5. Okay, so this is the argument here, right? If P, then Q. If R, then Q. If P, then R. Okay? Now, this is really, really important. When we're trying to see whether there's a counterexample, we are not going to try to prove this. Okay? We're not actually trying to build the actual conclusion. We're trying to see if we can build the opposite of the conclusion, right? So in other words, we're saying like, okay, if I start off with the exact same premises, that's just up here, can I end up in the opposite spot? Because if I can, that means that this argument that's currently on the page is a garbage argument, right? It has within it seeds of its own destruction. So what we're going to try to do is we're going to keep these premises up top the same, and then the conclusion down here, we're going to see if we can get to the opposite of this conclusion. So the conclusion here is if P, then R. But now take a look at what happens when, whoops, when we jump over here. What they are asking us to see if we can make is not P then R, right? So that's the opposite. All right, so how do we do these kinds of problems? They're actually pretty straightforward. And I think this starts off in exercise 4. They are giving you problems like this. What they want you to do is break these things down as explained in the chapter. And the way that you do this mechanically here is going to look something like this. There we go. Good. Okay, so you are going to select each of these formulas, right, by itself, and then you're going to select where you would like it broken down. Now, where we would like it broken down is on a new line here at the bottom of what we already have. And then you figure out what is that formula that you're looking for. What's the top level connected? In this case, it's a conditional. You go over on the side, you see that little conditional sign. All right, so this is deconstructing. So we are going to deconstruct a conditional. This is a conditional we're deconstructing, and here is where we are deconstructing it. And we're going to hit the apply button. You get a check mark next to the thing that you did. Then, because it's a conditional, it branches out into two options, not P and Q. Okay, cool. Can't really do anything with that yet. So let's move on to the next one. We pick the next formula right here. It's another conditional one. So where do we want to take it apart? Well, we want to take it apart on every branch that we can. So in this case, there's 2 branches, and it's again a conditional deconstruction, and we're going to apply that. Now notice that now each one of these branches is split into multiple other branches. All right. Now, so far, so good. What we are looking for our analysis is going to be whether or not we can find a contradiction, right, in the atomic elements here. So anytime that you have a statement that can't be true, because it would both have to be true and false simultaneously, that's the ideal version. All right, so all we have left is this is a negated conditional, and we want to take it apart on all 4 of the branches that we have, and you click on the negated conditional deconstruction, and we hit the apply option. All right, let's take a look. On this leftmost branch over here, we have not P, that has to be true, and then not R has to be true, and then P has to be true, and not R has to be true. Okay, so not R and not R, we're good with that, but both P and not P have to be true. Now, this would break the law of non-contradiction in logic. It's one of like 2 laws that are sacrosanct as you do logic. The idea is pretty straightforward. Nothing can both be true and false simultaneously. And you can sort of try to imagine it this way. If I say that you are watching this video and you're not watching this video, both of those statements can't be true at the same time, or in the same way, or in the same sort of general sense. So you might be thinking to yourself, well, I'm watching this video, but really I'm just listening to it. I'm not really watching it. Well, that means you're using the word watching in 2 different senses, right? So either you've turned on this video or you haven't, right? It's one or the other, never both. So when you find a contradiction like that, not P and P, you select both of them. You click the bottom of that branch, and then you click this little plus button here on the side. Now, what happened here is we ran into a dead end, right? In order for this branch to be true, we would need 2 contradictory statements to both be true simultaneously. That can't happen. So when you hit sort of a dead end on it, you hit closed. That tells you that that line of thinking isn't going to work. All right, let's look at the second branch here. Not P, Q, P, not R. All right, again, we have the P's in contradiction. So we select where the problem is, that's P and not P. We select the branch that it's on, and then we select that it's closed. So that line of thinking isn't going to work either. What about the third branch? Well, here we have Q, not R, P, and not R. Are any of these atomic statements in contradiction with one another? And the answer is no, right? We have P, Q, and not R. None of them have a contradiction. So in this case, you're going to click on the branch, click on the little plus sign. Now this branch is open and complete. What we mean by that is that all the values here could be true, and they would give us, from the same premises, the opposite of what the initial argument was about. Remember, the initial argument is that we're going to get if P, then R. Well, here we can get not if P, then R, right? So the opposite of what was argued. So an open branch means that when you've broken everything down, it actually works. You haven't run into a contradiction. Then we take a look at the fourth line, and we have Q, Q, P, not R. Again, no contradiction. So click on the branch, click on the plus sign. This is open and complete. So remember, what we were trying to see is find out whether or not there was a counterexample to this argument, which is why we flipped the conclusion around. Now, if you flip the conclusion around and everything ends up being closed, that means that there is no way of getting to that opposite conclusion. And that means that there is no counterexample to be given. But if you have open branches with the opposite of where you were trying to go initially, which was here, that means that there is a counterexample. These, in fact, are the counterexamples. So we're going to tell it, okay, there is a counterexample. Cool. So now we have to, we need to read a truth value assignment from a branch that provides a counter argument to the argument, or counterexample to the argument. So you click on the plus sign, you tell it to read. Okay, so what has to be true? Well, Q right here, you have to click on the letter. Q has to be true. Why? Because, well, we're looking at the truth value assignment that makes the counterexample work. So Q has to be true. P also has to be true. Okay, well, so why isn't everything true? Well, because some of the things are a little screwy, right? You see this not R. So if not R is true, then R must have been false, right? So R is false, and then the negation makes it true, and that's what will make this counterexample work. Ta-da, there we go. Now we are, now we're done. So we hit the close button, and that is the complete version of this problem. Obviously, if all the branches are closed, then there is no reading necessary because there is no value on which the counterexample exists, because there is no counterexample. Right, so that's about it. There is nothing else here. If you guys have any questions or comments or anything else for that matter, you can leave it in the comments, or you can feel free to email me, and I will see you next time with chapter 4. Take care.